Okay, right. So I'd say explicit level imports, that is something that is motivated by industrial usage, like work, untyped raw template Haskell. Intentional analysis, like type template Haskell, that is something that is more tender. That is something that I have just dedicated many hours to thinking about over the years. I wrote my PhD thesis about it. So this one is more of like a personal project, a distraction from the difficulties of the everyday world. So what have I been theorizing about type template Haskell recently? So to recap, if you have an expression of type T and you wrap it in a type template Haskell quotation, then the result is a representation of the expression E. And this representation is type indexed. So you can then manipulate these representations in your using quotes and splices in order to generate programs. That's not what this talk is about. That is lots of literature about doing that. I've written things about doing that, given talks about doing that. But I'm interested in whether I can use type template Haskell quotations, but for other things other than just generating programs. So the first difficulty in using this representation type to do anything else other than generating programs is that it's opaque. So once you have quoted an expression, there's no means to, unless you use unsafe backdoors, to inspect what that quotation is or learn anything in particular about it. You quote it, you know it's an expression which has type T, and that's all you have. Nothing else for you to learn there. So I want to use these, like what kind of analysis tasks do I want to do? Well, the first one I want to use it for is template Haskell, which I don't need any particular internal analysis. But I might want to write some kind of optimizer, which does some kind of source transformation of my terms before I insert them back into my program. Or I might want to serialize like a normal Haskell term if I want to send it over a network or things like that. And at the moment, quotations are unable to perform that task. The second issue the thing which could be improved is that this representation type is specific to template Haskell. It is completely overfitted to what is needed for type template Haskell. And when we're designing programming languages, we probably instead want to be designing general tools which work for our use case, but also fit in nicely for other things people might want to do. So I quite like to use this quotation, but for other purposes other than template Haskell. So number one, template Haskell, but maybe I want to send an expression over the network in a distributed computing scenario, and it would be quite nice to do that by using a quotation as well. Or perhaps you have your own DSL, which has some common programming language features, such as functions and applications and so on. And maybe it would be nice if you could write terms of that in a Haskell-like syntax, use a quotation, and then convert it into your DSL and do whatever you normally do with it, rather than having to use combinators. So I've been working with Ellis on this project, and we've been thinking about, what actually wouldn't be necessary to change in the design of type template Haskell quotations in order to allow us to achieve these two goals. So in order to solve problem one, we think we will try to use a PHOAS representation for representing programs rather than an opaque representation. PHOAS is just a common technique for embedding languages into Haskell, which stands for parametric higher order abstract syntax. And once we have done the first part, that brings into scope more problems that we need to solve. And in order to make it possible to use with for things other than template Haskell, we need to allow a means to extend the type checking of quotations. Because when you're using quotations in other contexts, you probably have different rules that you need the type checker to use. Right. So what is a PHOAS encoding? So this is a very simple language represented using a PHOAS encoding. What are the key parts of the PHOAS encoding? The first one is the type of variables is abstracted by this type parameter v. So v is of kind star to star. It's indexed by a type, and that is what the type of the variables are type of locally bound variables are in the representation. That is the characteristic part of parametric higher order abstract syntax. It is type indexed, which is critical for our use case because we want to perform well-typed optimizations, or we want to perform well-typed decoding. We want to have the same guarantees that type template Haskell provides you, but with the ability to perform additional modifications as well. And the higher order part of this abstract syntax is that functions are represented by functions in the host language. And the function here, the constructor here, lambda, takes a Haskell function where the argument is a variable and it produces another source term. So this is going to be what the representation of our template Haskell quotations is going to be. So how do we construct these PHOAS terms? Well, how do I construct a term that represents unit? Well, the type of that is going to be source v unit, and you represent it by using the unit constructor. For ID, that's using the lambda constructor. So the lambda constructor takes a Haskell function as the argument, and the type of x here is v applied to a variable a. So in order to embed that back into the source language, you have to use the variable constructor. And then for applications, well, we use the application constructor. So representing terms in this way, I've made to appear is extremely straightforward, I would hope. So now, we have refreshed ourselves. Rodrigo.
So when is v instances something?
When you do the interpretation, the question is when is v instantiated something? The answer is when you do an interpretation. And when your interpretation function instantiates v into what the result type of the interpretation is, which I'll get to some interpretations shortly. Right. Okay, so I've now explained how to represent some simple terms using PHOAS. Well, now we turn to the question of how do we desugar a template Haskell quotation to PHOAS? Well, if I quote the unit, then I'll represent it as unit. That's nice and simple. If I quote a lambda, then why don't I represent that as a lambda in my PHOAS encoding? And if I have an application, then why don't I represent that as an application? So that's the kind of core idea of our proposal, is to represent terms in this manner. Right. Any questions about that kind of question?
If SID is not polymorphic in V, would that propagate, or would you require it to be for all?
Yeah. So it would. So the question is, if this this variable SID was not polymorphic in V, would that propagate? And the answer is yes, it would propagate. Okay. Right. Okay. So now I have my new representation for type template Haskell quotations. So what can I actually do with these, which I couldn't do before? Well, first one is the identity interpretation, and what this says is give me a representation of a Haskell value, and I'm going to turn it into a Haskell value. So with template Haskell quotation right now, once you have that representation in your hands, you can't turn it back into the value that you quoted originally. So but this is not why you would not. I'm not necessarily sure why you would do this, but it's certainly possible. I can imagine people would. An optimizer takes a source expression and produces another source expression. And here the v parameter is instantiated to the source expression type. For template Haskell, the parameter is going to be code Q, which is the type constructor for existing template Haskell representation. And for serialization, you might use this byte string new type, which has a phantom type parameter, and you can turn your source program into a byte string. Right. So that's the principle of the idea of the talk. Yeah.
Would this enable a typed verify?
Typed verify.
Yeah.
So the question is, would this enable typed verify? What's the API for typed verify?
Or currently there is verify, which is given a name of a type, for example, and gives us template Haskell. I guess
Yeah.
in case of type, but for expressions it doesn't really do anything. So I'm wondering if this would enable verify to be more precise.
Yeah, so the question is about verifying whether this will enable it to be more precise or change the API, and I don't know the answer, to be honest. I'm not very familiar with that part of the API, but probably it might do. That's a good. That's the sort of thinking I'm hoping to inspire by this talk. Okay, so that is the principal idea, but then you actually attempt to execute this brilliantly simple idea, and you encounter complication 1 to 4, which we'll get into now. And the first complication is that Template Haskell allows you to quote open terms. For example, quoting an identity function the identity function here is free within the quotation. It is not bound within the quotation, so that requires like an additional something additional in our language. So the solution that we have now is to add another type parameter. So we have the E type parameter, which is for external variables, which is different to the V type parameter, which is for internal variables. So when you're using this for Template Haskell, then or whatever your usage, you need to make sure all your external variables have the same type. For Template Haskell, that will just be the name type. So that the type of this quotation is source name V, A to A.
Well, you could also augment your V, whatever you instantiate V at, right?
But you need, so Ben asks, can you modify V? And the answer is no, because you need to instantiate V when you do the interpretation.
Right, but whatever you use during interpretation could be a sum
Okay.
of external and whatever.
Yeah, so you could potentially reuse the V parameter if.
Okay, but there's no. This is more convenient, I guess.
Yeah, I mean, whether it's more convenient or not is still up for discussion. But we thought it was better to initially separate concerns and be clear about what the requirements were, rather than stuff it all together.
And I guess you could, if you wanted to represent a closed term, you could just instantiate E at like a void type with an argument.
Yeah.
Okay.
Right, so for Template Haskell, use the name, Template Haskell name for external references. For the runtime interpretation, you use the identity constructor, so you just have a pointer to something on the heap. For static pointers, use like the static pointer type that is what is used for external references. And so this part is what requires modifying the type checker, because as I explained in the last talk, very conveniently, there's all these rules that you need to use to ensure whether you're allowed to use external variables. And these rules are different for each of these three cases.
Is it name or const name? Because it doesn't change.
Name or const name?
Source name VA is a kind of...
Is it?
In the Template Haskell case, because name doesn't have an argument, right?
Oh, I see. Right, yes. Just imagine it does work. I mean, come on. Yeah, I think everyone here can imagine what I mean here. Right, come on. Okay, so complication 2 is to do representing constructors and cases, which are obviously conveniently left out the original explanation. And the idea here is to represent constructors using generics. And so we introduce a new part to the DSL, which says, well, if you want to represent your own constructor, it has to have a generic instance, and the fields of the generic construction are themselves source expressions. So in this representation of right unit, then that would be the sum of the product of SS, SZ, and then the unit itself is another example of a source term. So you go source term, generics, like so on and so on. In this loop. Okay, then for cases and pattern matching, again, we introduce a new part of the language, and that requires introducing clauses, and clauses require introducing patterns, and so on and so on. So it gets quite elaborate, like representing more and more of the source language in this way. And we've thought about like what we think are the interesting cases, but it does feel like quite a bit of work to like think about everything. So we'll see how far we actually get. Right. How much time have I got left, Loiter?
8 minutes.
8 minutes. Okay.
Including questions.
Cool. So complication 3, relevant type information. So if you attempt to implement these pair of encoding and decoding functions for this source data type, then you'll find that you actually get stuck with the definitions that I've given. And the problem is that when you try to decode from the byte string, you don't have enough type information stored within the term in order to reconstruct the term in a safe manner. So then you start needing to add additional type information about what the types of the binders are. In particular, on the lambda constructor, you need to record what the type of the variable is, so that you can implement a bidirectional type checking scheme with a check mode and an inference mode. So that's another slight. Is that ugly or is it not? I'm not sure. Just something just a complication, let's say. And then complication 4, the implementation. Feel like this is the main complication. There are several. Just modifying the type checker for me feels like quite difficult. So, like for example, expressions have got to have simple types in order to be represented in this scheme. That needs to be enforced in the type checker. The constructors have to have generic instances. They have to be saturated. These are in normal Haskell. Constructors don't have to be saturated. They don't need generic instances. It's just a complication about modifying the type checker to record that information and to store it somewhere where you can reuse it. And then the third complication is this thing to do with external references. You need to check different external references in different ways, and that requires some mechanism for ideally the user to extend the language to say what that is. For these cases I've said, maybe you can build in static pointers, Template Haskell, they're already built in. But if you want to use a quotation to generate C, well, then you probably need to have some means to, or if you want to generate a circuit, or so on and so on, you need to have some means to say which variables, external variables, are actually allowed to be used in a circuit or allowed to be used in your C program. And really, that should be for the user to write rather than the compiler writer. Unless you just want to be using the identity function. I might hard code that one in. Okay, so future work. There's this thing about the user extension, and also about the implementation I just said. And I mean, I have the secret hope that one day, it's not a secret hope, I'm not shy about it. I want to make type Template Haskell work properly one day, and I need for that a representation which stores type information in it in an orderly way. So maybe this will get me one step closer to that lifelong pursuit. But I still sense I have a few years ahead of me yet. So that's all for today. And any questions if people have them? Adam.
So, Surface Haskell is quite a big language, and it doesn't always have type annotations, whereas Core is a small language and does. So, I mean, why not do this with Core rather than with Surface Haskell?
The question is, why not do this with Core rather than Surface Haskell? Yeah, maybe that would be a better idea.
I mean, you're not even 10% of the way through Surface Haskell, as far as I can tell, right? I mean, it's like...
I thought I was barely 1% of the way through.
That's right.
I haven't got to typed bang yet, like Andreas was talking about, but we'll get there. Yeah, that is a very reasonable suggestion. I think we just started thinking of it in terms of source Haskell. But then we've only implemented things that exist in Core as well. So, yeah.
Core is much more within reach. But the question is, does it cover your use cases? I mean, for things like optimization and serialization, maybe it does.
Yeah, but I think like people generating, I don't know what people are doing, but I imagine for like generating things in DSL, you probably don't want to write a translation from all source Haskell anyway to your DSL. You might want to do it from a small representation, but and maybe that is better because then you also get the advantage of being able to write high-level features that compile to lower-level features. Go.
So what happens when you stray off those 10%? Like, what exactly fails? Is it just you have some catch or I don't know what?
Oh, well, I've not implemented it, so
okay.
So you write it in and literally nothing. Literally nothing happens. Yeah, the question was, what do you do when you stray off the 10%? And the answer was, well, the same as if you are in the 10% because it's not implemented, right? Yeah.
Why did you pick parametric paradox syntax over other representations of binding?
Because I think it is the most convenient one to work with and the best way to represent a language inside Haskell.
But no gadgets.
No,
GADT.
yeah, that's part of the compromise of being able to do the. You want to design something that is not too complicated, in my opinion, which represents a large amount of programs, but is I don't know. There's always a trade-off. It's just my opinion that it's a really nice way, and I think it's really nice because of this parameterization over the variable parameter.
But doesn't it complicate the patterns, handling of the patterns, the left-hand side?
Not really. No. One more question, or are we we're enough?
One or two more.
Yes, Kergo.
So about the idea of using core instead of surface Haskell, like, is it even possible to desugar a fragment of surface Haskell? Like, because I assume you would still write surface Haskell inside a quotation. Is it even possible to have core for a fragment that is inside the lingua?
Yeah, no, it's definitely possible to have core of a fragment. If you're using type quotations, definitely, because they get type checked, and then you just turn it into a core expression after they're type checked. Well.
Any more questions? Mario's still signing up.
Yeah, so we have implemented like a very, very basic proof of concept, but nothing that is serious.
Okay, let's thank the speaker.